Let's do another problem where we graph a function based on the properties of its derivatives and second derivative. And what's especially interesting about this problem, I think, is the fact that they don't give the function. They just give a bunch of clues about the function. So what do they tell us? Well, they tell us that f of 0 is equal to 3. They also tell us that f of 3 is equal to 0. F of 3 is equal to 0. They tell us that f of 6 is equal to 4. F of 6 is equal to 4. And what I like about this what I like about this problem is that you can't use a calculator to solve it because you don't know the function. So even if I gave you a graphing calculator, you'd be helpless. So anyway, let's write down all the information, then we could plot it out. They also tell us, let me write all the derivative information here. They tell us that f prime, so the derivative of x, is less than 0 on the open interval 0, 3. So that means not including 0 and 3. And they also tell us that the derivative is greater than 0 on the open interval from 3, 6. So we can already guess that if we're less than 0 as we approach 3, and we're greater than 0 as we go away from 3, that the derivative must be 0 at 3. That's the intuition. Although they don't tell us that for sure, but I'm assuming that this function is continuous and differentiable over all of the intervals because they don't tell us otherwise. Okay, so that's the information to tell us about the first derivative. And what do they tell us about the second derivative? They tell us that the second derivative is greater than 0 on the interval 0 to 5. Right, this is the open interval from 0 to 5. So that means it's concave upwards there. And they also tell us that the second derivative is less than 0, so it's concave downwards on the open interval from 5 to 6. So I don't know I don't know, they don't give us any information what happens after 6. Maybe it goes to an inflection point. We don't know. So maybe, we'll just assume that it doesn't change. So what does all this information tell us? Well, first let's just graph it. So f of 0 is 3, so we have to graph the point 0, 3, 3, 0, and 6, 4. So it seems like all of the action is in the first quadrant, so I'll graph it accordingly. So let me graph it. So I want to focus on the first quadrant. So that's my x-axis. That's my y-axis. Let's see, I have to go to 6, 4. So let's see if this is, draw this. So I want to draw this point, 6, 4. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So that's the point 6, 4. That's the point 6, 4. And let's see, 3, 0. Right? So that's 1, 2, 3. So that's this point right here. That point right there is 3, 0. 3, 0. I got that from this information. And then we have the point 0, 3. 0, 1, 2, 3. So this is 0, 3. 0, 3. So those are the points that they tell us that something, those are definitely points on the function. That's what this tells us. And what do they tell us? They tell us that the derivative is less than 0 on the interval from 0 to 3. So from here to here, the derivative is less than 0. From here to here, the derivative is less than 0. And that makes sense because we had to obviously decrease to go from this value to this value. But what it does tell us is that the function does not do something like this. The function does not do this. The function does not do that. And how do we know that? Well, because if the function moved up and then down, then you'd have a positive slope here, which this says is not possible, right? The derivative is less than 0 from this interval to this interval, so the slope has to be negative the entire time. And then it tells us that the slope is positive from this interval, from x is equal to 3 to x is equal to 6. That's what this tells us. And so, the line has to look something like that or like that. But it can't curve down and then go up, because if it curved down, you'd have a negative slope at some point. So, okay, fair enough. It's essentially the graph is monotonic from this point to this point and this point to this point. And if you want to get technical, the monotonicity theorem tells us that, well, then this must be a point either that is a point where the derivative is 0, or it must be a point where there is no derivative. But I'm assuming that this graph is differentiable over everything. And you didn't need the theorem to tell you that. We know that the slope is less than 0 as we approach here in this interval, and we know the slope is greater than 0 in this interval. And if we assume that the derivative is continuous, which I will make that assumption, although they haven't told us, but in the absence of that information, why not? If the derivative is always kind of incrementing or decrementing at a continuous rate, the derivative must be 0 at this point, right? Because it's less than 0 here and greater than 0 here. So I'll draw a little horizontal line to indicate that the derivative is 0 there. So it's going to be a bit of a minimum point, I think. And then let's move on to the information on the second derivatives and see what they're telling us. Well, they're saying that the second derivative is greater than 0 from 0 to 5. So from 0 to 5. So this is 5 right here. From 0 to 5. So essentially that means, what does this tell us? This means that we are concave upwards from 0 to 5. So concave upwards, that gives us a lot of information. So that tells us that not only are we monotonically decreasing as we approach 3, but we're concave upwards, right? And why is this concave upwards? Well, as you see, the slope here is negative. It's a little less negative here, even less negative here, and then it slowly approaches 0. It gets less and less negative, and then it keeps increasing until you get to 5, right? And then from 5 to 6, what happens? The second derivative becomes negative. So we enter a point that is concave downwards. So from 5 to 6, I don't know what the value of the function is at 5, but from 5 to 6, the function, let me pick a suitably different color, becomes concave downwards from x equals 5 to x equals 6. So it becomes concave downwards. So f of 5, we don't know what f of 5 is, but f of 5, they didn't tell us, is an inflection point. That's where we went from going concave upwards to concave downwards. And I think that's all we can do with this graph. We don't know what happens. I mean, actually, we made a couple of assumptions anyway, that the graph is continuous and differentiable over the whole thing. But anyway, I think this will give you an intuition on what all of this, first and second derivative and all of this stuff does for us. And, just so you know, as if this was an inflection point, they could have told us that f prime prime of 5 is equal to 0. We don't know that for sure, but I'm just assuming it. Well, anyway, hope you found that vaguely useful. Actually, since I have time, let me do one more bonus problem that I was sent, and it was written right after that problem, so why not do it? And it says, prove that a quadratic function has no inflections. What does a quadratic function look like? F of x is equal to a x squared plus bx plus c. And it says, prove that this has no inflection point. Well, what's an inflection point? It's a point where the second derivative is equal to 0. So let's figure out what the second derivative is. The first derivative of a quadratic, of this quadratic, but any quadratic can be written like this, is 2ax plus b. And what's the second derivative? Well, that's just equal to 2a. Now, an inflection point is when the second derivative is equal to 0. Now, my question to you is, can this function ever equal 0? Well, the only way that this function would equal 0 if for some reason a was 0, but if a was 0, then it wouldn't be a quadratic, because then this term wouldn't exist. It would be bx plus c, and it would be just a line. So if we're talking about a quadratic where this a coefficient is non-zero, which it has to be, because that's the coefficient of the x term, there's no way that if a is non-zero, there's no way that this function, this expression is non-zero. So there's no way that the second derivative can ever be 0, and thus we have proved that a quadratic has no point of inflection. See you in the next video.